Yes, thank you, Ransan. Good day, good afternoon, good morning, hello to everyone, and welcome to the webinar devoted to the latest developments in beta radiation metrology. And thank you for joining us today. I am very pleased to introduce our speaker, Dr. Rolf Behrens from the PTB, with a lot of years of experience in beta radiation dosimetry. He is the head of working group on dosimetry for brachytherapy and beta radiation protection. And also, Dr. Behrens is strongly involved in national and international standardization as a head or a member of many working groups and committees related to dosimetry. And in particular, he is the head of Iciu working group on beta reference radiations. So now let me give a word to Rolf himself. So please, let's start.
Thank you very much, Vincent and Anna. I hope you can hear me well. You can understand me?
Yes.
Perfect.
Everything is fine.
I will start presenting my talk. Now you should see it.
Yes.
Perfect. So as announced already by Anna, thank you. Latest developments in beta radiation metrology. Let me have some forwards for the presentation. Scattered all over the presentation, there are hyperlinks written in light blue and underlined, like this here, for example, or hyperlink to our department's website at PTB. As already mentioned, the PDF of the presentation, together with all these hyperlinks in there, will be available together with a video at CCRI's website. Firstly, I would like to thank for the invitation, and I'm really honored to be member or part of the CCRI webinars. This is the contents of my talk. After a short introduction, I will address primary and secondary beta dosimetry. Very shortly mention the currently running international comparison under the BIPM Euromed umbrella in beta dosimetry. Then the main part of my talk will be the revision of the ISO 6980 standard series for beta reference radiation fields, and closely connected with this correction factors for beta dosimetry. And finally, I will have some words on the newly proposed operational quantities according to Iciu 95, especially related to betas. Just to remind you, different types of particles have different penetration abilities. The main difference between photons and charged particles is that photons have a finite penetration probability with unchanged energy, while charged particles continuously lose energy and they have a finite range. So you see here a lot of scattering for electrons in this case, and during every scatter a little bit of energy is lost, and so in the final end energy is completely lost and the range of the particle is reached. Here you see a scarred and doubled logarithmic scale, ranges of charged particles in air. Here you see, for example, 1 MeV electron penetrates a few meters of air. This is a principle, the same range for positrons. If you go to the nuclear data service of IAEA, then you can enter here, for example, strontium-90, and you get the radionuclide information here. It has got a half-life of nearly 29 years, decays with beta to yttrium-90 with 64 hours half-life, which decays to zirconium-90, which is stable then. So here on the chart of nuclides, to the upper left, there's a beta minus decay, and to the upper lower right, there's a beta plus decay releasing positons. As mentioned before, electrons and positons have practically the same interaction patterns apart from the positons end, which is a recombination with another electron to form annihilation radiation, 2 gammas of 511 keV as well known. Beta particle spectra, so from beta decays, usually a complete range of spectrum is emitted, and beta particle spectra are contained in ICRP 107. Here you see 3 examples with different endpoint energies. Here only 18 keV, 156 keV, and 1.7 MeV for phosphor 32 in this example. Beta radiation is used in different areas, for example, in industry for process control here, especially thickness process with different nuclides. These nuclides have increasing beta mean energies. You see here the scar of beta mean energy, and it's used often, very often in medicine. For example, a very important nuclide, Iciu 90, used here for radiosynaptosis for pain therapy in a knee, or also for tumor treatment. Ruthenium rhodium eye applicators are fixed to an eye for several days and then remain there, irradiates the tumor, and are removed again. This has a rather large beta mean energy here. Primary and secondary beta dosimetry. Beta radiation has the effect that significant absorption and scattering is already present in rather small air volumes. Here we have an air cube of 1 by 1 by 1 centimeter of air. And you see here 10 keV photons are penetrating nearly unaffected through this 1 centimeter of air, while 10 keV electrons scatter a lot of have a lot of scatter events and are totally absorbed within the first few millimeters. Here's a radiation also, like for the photons coming from the left to the right. Therefore, ionization chambers used in beta dosimetry are formed by a blunt parallel chamber with a very thin depth here, principally a thin, shallow slice of active air volume. Such an ionization chamber was developed at that time at PDB, the so-called Bohm chamber, and this is commercially available by company PTW, a German company, and is worldwide in use. These chambers are called extrapolation chamber because it's possible to vary the chamber depths, in this case for the Bohm chamber from 250 up to 2,500 micrometers with an area in diameter of 3 centimeters. So this is not to scale here, of course. It's a very shallow slice, the active air volume. When varying the chamber depths here, you can measure the ionization current, and depending on the chamber depths, applying all necessary corrections, this forms, if corrections are appropriate, a linear curve. This linear curve is extrapolated to 0 depths, to the slope here at 0 depths. And this slope of the ionization current with the corrections is then used to determine the absorbed dose rate in tissue, which is a basic quantity according to this ISO standard series. To arrive from the ionization current to the dose, you need the mean energy per electron air hole. Here, the stopping power ratio from tissue to air, because you measure in air and are interested in the dose in tissue. And here, this is in principle the mass of the air volume, the active air volume here, the density of the air, the area of the chamber, and the thickness of the chamber. So this is in principle the of absorbed dose. In this case here, as mentioned, And unfortunately, in reality, you do not always have a perfect linear behavior of the extrapolation curve. For illustration purposes, it is enlarged by a factor of 10 here. And therefore, in this ISO standard, it is allowed to use the quadratic fit to obtain the slope here at 0 depths. Just, I would like to now I think you can see my laser pointer a little bit better than the mouse itself.
Yes.
Fine. Okay. As mentioned before, here you have many different correction factors. And here I give you a list of all these correction factors, list from the current draft of this ISO standard. I will address some of them, I hope the most important later on, but will not go into detail for all of them now. When having measured with the extrapolation chamber, different absorbers of different thickness are placed in front of the extrapolation chamber in order to be able to perform an interpolation to relevant tissue depths. So this is the dose rate depending on the tissue depth, as you can see here. Tissue equivalent depths on a logarithmic scale, and you see the dose rate here interpolated to 0.07 millimeters, which is relevant for the quantity HP 0.7, and here HP3 in 3 millimeter depths. The dissemination of beta radiation dose is achieved by a complete irradiation facility, which was also developed at PDB at that time and is commercially available by another German company. The so-called beta secondary standard, and this one in the second version. All radiation sources coming with the secondary standard are traceable to PDB. That means they were calibrated in our primary lab. All the doses you irradiate here, for example, on a ring dosimeter, or on the left on a whole body dosimeter are quality assured, and all parameters with, during the irradiation are computer controlled. So by this, you have a complete irradiation facility available. It's the beta secondary standard. The standard configuration covers this energy range between below 100 keV and 0.8 MeV, and different dose rates by variation of the irradiation distance, as you can see here. To notice there's an energy gap between this krypton source here and the strontium yttrium source here. Just to notice, this strontium yttrium is the main working horse in beta dosimetry, because, as mentioned before, the strontium has a rather large half-life of 29 years, while the yttrium emits a spectrum which is of very high importance in medicine. Therefore, this is a very important and radionuclide used in beta dosimetry. At PDB, we have upgraded our BSS2 with a ruthenium rhodium source at different distances here to enlarge the energy range to the upper end. Since the 1980s, this in the first version, it is distributed worldwide and used in many different labs, as you can see here. Just one further detail of the BSS2. Here you have the radiation source, and in this place is an ionization chamber, a secondary ionization chamber of rather large dimension. And when using the pure source, you have this dose rate profile here. You see here the radial position in the phantom, so in the beam area here at 30 centimeter distance from the source, you have a beam dose profile as shown here. in 0.07 millimeter tissue depth. At 3 millimeter tissue depth, it looks like this, the dose profile here in the color code indicated. And when placing a so-called beam flattening filter, laser pointer is somehow delayed. When placing the beam flattening filter here in position, appropriate thickness, of course, together with its source, then you have a rather nearly perfect homogeneous beam profile in the beam irradiation area. Now I will shortly mention the international comparison running under the BIPM Euromid umbrella. It was started in 2018. We performed the comparison for the two basic quantities, HP 0.07 and HP3, the latter for the first time. And we circulate a secondary standard ionization chamber, developed also measuring stand. And in total, we did so to 16 participants. The last participant, Cuba, is currently performing measurements, and the report is expected next year. Now, before I come to the main part of the presentation, just a short feedback. You still hear me? Everything fine?
Yes, everything fine. Thank you.
Perfect.
Very interesting.
Thank you. Thank you. Okay, so now we come to the main part of the presentation, revision of the ISO 6980. This standard series on reference beta radiation field is maintained by the ISO working group TC85 subcommittee 2 reference radiation fields, working group 2, which is chaired by Oliver Hupe. The standard 6980, the part 2, describing the basic dosimetry, was issued in 2004, and the part 1 for method of production of the radiation fields and the part 3 for calibration of devices were issued in 2006. And to notice, nearly all correction factors contained in these standard series are based on measurements using a beam chamber. Since May 2019, the standard series is in revision. And let me firstly address some minor editorial changes. First, we align the standard to the general one on reference radiation fields from the working group 2, 29661. Secondly, we include detailed graphs of particle spectra for both electrons and photons. Detailed graphs will follow later on in the presentation. We will harmonize the irradiation phantoms, here the isowater slab phantom and the isocylinder phantom for eye dosimeters. And this will be harmonized by a substitute 20 by 20 centimeter in cross section and 2 centimeter in thickness made of PMMA, because such a plate is sufficiently thick to mimic the backscatter of the human body in the case of beta radiation. Of course, this is different to photon radiation because betas do not penetrate more than 2 centimeters of PMMA, as shown before. We will include the photon contribution, which is for some nuclides very small, but rising up to approximately 0.5% for promethium sources. And finally, we will remove carbon-14 sources, which were covered by the current standards version, but it has a rather small mean energy, beta mean energy, and is not in use in any institute. Therefore, we remove it. Now we come to the major technical changes, namely correction factors by means of simulations. The starting point for the simulation is, in this case, the source of a beta secondary standard, and the radiation is penetrating here to the bottom of the big plane. In reality, of course, this is a horizontal beam in reality, but for the sake of cleanness in the presentation, I made it this way. In reality, you have placed the extrapolation chamber in front of the source, as outlined before, to determine the absorbed dose rate to tissue, which is equivalent to the HPO.7 slab phantom. And in the simulation, this is replaced by an Iciu 4-element tissue slab, 30 by 30 by 15 centimeter cubic. And with this, you get the basic quantity HPO.7 in a tissue slab. So this is a basic quantity in beta dosimetry. To enhance the simulation efficiency, phase-based files were produced for the different radionuclide sources here. And all these phase-based files and also ASCII files from the Spectra as reference planes are freely available within these publications here, which are all open access in Journal of Instrumentation. In the past, there was no difference considered between the large slab phantom, on the other hand, between the small rod phantom, and also not for the area quantity H prime 0.07, all were taken as being equally. And in the new standard version, in the revised version, the difference will be considered by calculating also the dose at 0.07 millimeter depth here in the rod and in the Iciu sphere. And so you get these correction factors to account for the different phantoms and quantities. Furthermore, the quantity HP3 and H prime 3 will be included in the new version of the standard. This is the SCAD of nuclides and distances, which is covered in the current version of the standard. You see here, for example, the carbon-14 still in. And in the next version here marked in white, therefore, this will be removed, and some more different distances for ruthenium especially will be included in the new revised version of the standard. In addition, the Japanese colleagues suggested to use the strontium yttrium source behind absorbers made of 3 or 4 millimeter PMMA placed in front of the source in order to get energy reduced radiation fields. So what I mean is this, the energy and dose rate ranges covered in the current version of 2004-2006 is this one here. And in the new version, this will be the range which is covered. You see here the additional radiation fields which were suggested by the Japanese colleagues and also the ruthenium source. You may have seen that the carbon-14 source below here was removed, as mentioned before. Also, I mentioned that particle spectra will be included in the new version. So you see here electron spectra on the left and photon spectra on the right, both on a linear scale. In this case, 3 in air, that means without any backscatter. And all these spectra are normalized to a dose of 1 millisievert HP 0.07. On a logarithmic scale, here you see the clear domination of the photon spectra by the Bremsstrahlung contributions and added up with several gamma lines, especially for ruthenium-rhodium source, as these nuclides emit gammas, as you can see here. As mentioned before, these are the particle spectra free in air, but in beta dosimetry, a tissue phantom forms a basic geometry, and therefore I also calculated the spectra in front of a tissue phantom. So no further absorption, but only the backscatter from a tissue phantom is what can be added, and this looks like this. You may have seen that the promethium source here is a little bit, spectrum is a little bit larger, likewise for the photons, but no absorption is in place now. As mentioned before, 0.07 millimeter in the tissue depth is of most interest in beta dosimetry. And here you see the promethium spectrum is significantly absorbed, while the others, krypton, the energy reduced strontium sources, the black one, the strontium, yttrium, and blue, the ruthenium spectra, are not so strongly absorbed. Of course, you can see this spectra here not so good. Therefore, I enlarge the ordinate by a factor of 4.5, and you see the different spectra as interesting or most relevant tissue depths of 0.07 millimeter, as you can see here, which is relevant for the quantity HP 0.07. And moving further down in the tissue slab to 3 millimeter depths, you see another significant absorption. Promethium and krypton, their betas are totally absorbed, and the others are also significantly absorbed, but you have spectra remaining here. Now we come to the second major technical change, namely corrections for correction factors for primary dosimetry. They were undertaken for all the radiation fields given here on this SCART. As mentioned before, the so-called Behrens chamber was developed at that time at PTB as primary standard. You see it here in a housing made of PMMA, which forms a slab, and as outlined before, is then converted to tissue equivalent dose. And in recent years, PTB developed a new primary standard. I call it beta primary standard number 2, which is located here in the housing of another plastic. It's macrolone. All the following correction factors were calculated for both of these chambers. In this radiation geometry, in this case now in the horizontal mode, orientation, I show you the model of PTB's new primary standard. You see here the active air volume in the very front, of course, because a very thin foil, entrance foil in the very front. So you have here the active air volume, diameter 3 centimeter, and variable volume like at the Behrens chamber again. The same. Behind this, we have a 2 millimeter plastic, in this case polyether ketone as an insulator. And behind this, there's a nearly 2 centimeter plastic, but electrically conducting. This is achieved by doping the peak with carbon nanotubes, which makes it electrically conducting. This conducting slice of 2 centimeters prevents room charges behind the active air volume, and therefore is supposed to improve the measurement signal. So now we come to some rather important correction factors. Firstly, let me address the correction factor for backscatter. So you have here the real chamber, which scatters back into the active air volume. But of course, you are interested in the dose and tissue. Therefore, the chamber backing was replaced in the simulation by a tissue back. And the dose and the active air volume with the tissue bag was then calculated and divided by the dose with in the active air volume by with the real chamber bag. And the corresponding ratio is the correction for backscatter. Next one is a very important, I think most important correction factor for sidewall perturbation, KPE. This is the dose in the active volume here, and then the ratio is built with the dose without the chamber walls. because you're not interested in a dose in a chamber with walls made of plastic, but yeah, in the pure air volume, which is then converted to tissue dose. So this ratio here, dose in chamber without walls divided by dose in real chamber, is a correction factor for perturbation, for cycle perturbation. The next one is a correction factor for inhomogeneity. Of course, this active air volume of 3 centimeters in diameter and up to 2,500 micrometers in thickness is of finite size, but the dose is a point quantity. And therefore, in principle, you need to determine the dose in a point, which is not possible in Monte Carlo transport simulations, which were, by the way, all undertaken using EGS NRC. And therefore, a small, nearly point, a small, very thin slice, which is present here, but not to see, was positioned here in the front. It has a diameter of 0.5 centimeter and a thickness of 100 micrometers. This cannot be seen instead of the magnification of a factor of 4. Therefore, let us have another factor of 10 to sum up to a magnification, a factor of 40. And then you see this small slice, which is considered as a point in which the dose calculated and the ratio in this very small volume divided by the ratio in the complete volume is then the correction for beam for inhomogeneity of the radiation beam. Finally, some Indian colleagues undertook the sophisticated Monte Carlo transport simulations regarding the Bragg-Ray and Spencer ethics theory. As outlined before, in the basic quantity for absorbed dose to tissue, you have got here the stopping power ratio from tissue to air. Just to remind you, because you measure in air and are interested in the dose in tissue. And the stopping power ratio can be calculated, or what is calculated in the current version of the standard according to the Bragg-Ray theory, which does not consider the volume of the ionization chamber of the cavity. In contrast to this, the Spencer ethics theory does consider the dimensions of the active air volume, and the Indian colleagues undertook these simulations and calculated the stopping power ratio based on the Spencer ethics theory, and then we calculated the ratio to the stopping power ratio according to the Bragg-Ray theory, and this is a new correction factor considering the changing from Bragg-Ray to Spencer ethics theory, which will also be implemented in the new version of the ISO standard. Now you may wonder, well, all these new correction factors, are they better now? Is the nonlinearity of the extrapolation curves, is it better now? Is it solved here, this problem? And the clear answer, at least for some examples here, is yes. Let us have a look at Krypton 85 sources. Here you see the deviation from a linear regression in percentage. And you see that when applying the current version of the standard as of 2004, you have a significant and systematic deviation from linearity, while when applying all these correction factors determined with EGS NRC, you end up in a nearly perfect linear curve. This is even more dramatic when having a look at oblique radiation incidence. So here in this example for strontium yttrium source at 60 degrees radiation incidence, then you have this deviation from linearity when applying the current version of the standard, and the new correction factors will correct the extrapolation curve nearly to linearity. Just to mention, to be honest, the current version of the standard is not valid for oblique incidence. I applied here the correction factors for 0 degrees to the 60 degrees measurement, so it's in principle not 100% pure. this improvement, but it is a case that in the new version of the standard, these correction factors will also be available for oblique radiation incidence up to 60 degrees. So to resume this part of the talk, in the current version, nearly all correction factors are based on measurements, while in the new version, at least some very important correction factors will be based on simulations. The current status of the draft series of the standard series is that the FDIS, the final draft international standard, was circulated for vote in August of this year, and comments can be directed to ISO until the beginning of October, so the commenting time is still running. After that, the final standards, the international standards, will be issued in the new version, possibly end of this year, probably beginning of next year. Just here a list of some references related to the revision of the ISO standard series. And as you see here, in May 2019, we had the very first meeting regarding this revision in Okayama in Japan. And then, as all of you know, COVID came in, which enabled us, of course, to have some more meetings than we would have had if COVID had not jumped in. So very efficient and fast way to produce new versions of the standards. Finally, let me have some words on the newly proposed operational quantities according to Iciu 95. This report was issued some 2 years ago, and last October, so last year in October, there was a CCRI webinar by Thomas Otto presenting in detail the changes due to the new proposed operational quantities. I warmly recommend you this webinar. The PDF and the video are available on CCRI's website. A more recent contribution I was able to present at the individual monitoring conference in this April, and on PDB's website we have also available the PDF and the video of that presentation. Anyway, I would like to give rough overview of this report and the new things in it, but for details I refer to these two presentations shown here. Just very briefly, to remind you, protection quantities in radiation protection are defined in ICRP 116 publication. Effective dose in the voxel phantom, islands dose in the stylized islands model phantom, and local skin dose in a simple small ICIU tissue cube. The current operational quantities according to ICIU 51 and 57 are for area monitoring defined in the well-known famous ICIU sphere made of ICIU 4-element tissue at different depths for area monitoring, and in the person to be monitored for individual monitoring at corresponding depths. For calibration purposes, phantoms made of ICIU 4-element tissue as well formed, and the corresponding dose quantities conversion coefficients are calculated in these phantoms for the current quantities. As you can see here, these are very different definitions here for protection quantities on the one hand and operational quantities on the other hand. This is cleaned up, as Thomas Otto says recently in a presentation. This is cleaned up with ICIU 95, where all the same phantoms will be used for operational quantities as is the case for protection quantities. Let me shortly explain the method of primary dosimetry for operational quantities, in this case for neutrons. The basic quantity is fluence. Then you need to determine the spectrum, however, either by measurements or simulations. And with this particle spectrum, depending on neutron energy, this is then folded with conversion coefficients from monoenergetic neutrons, which are contained in the corresponding ICIU reports, currently ICIU 57, and for the newly proposed quantities in ICIU 95. And then these conversion coefficients, together with the spectral neutron fluence, are integrated to form the operational quantity. These are the definitions of the operational quantities in short here. This is rather similar for photons. Here you need the spectrum as well. Fold them this with the conversion coefficients for monoenergetic photons, because in photon dosimetry, air gamma is the basic quantity. You additionally need the so-called Kerma factor, Kerma divided by fluence, energy dependent, but these are also contained in ICIU 57 and 95, and so you can form this integral here and end up with the operational quantities for photons. For beta dosimetry, this is different. The reason is following. In this case, you have an air cube of 1 by 1 by 1 meter. And here from the left to the right, with an certain opening angle of plus minus 11 degrees, photons are penetrating here. I made some graphs here for different energies, as you can see in the top. And yeah, this is the case for electrons with many scatterings as outlined before. And photon in the beam center, the photon fields are practically monodirectional, and therefore it is possible to fold the spectrum measured in the beam center with the conversion coefficients for specific angles of radiation incidence, so for normal incidence or other angles of incidence, to end up with the operational quantity. In this case, for photons, for neutrons, this is similar. But for electrons, the radiation fields are far from being monodirectional. And therefore, this folding with the conversion coefficients makes a lot of problems. You had to consider all these different angles of incidence and energies as well. As mentioned before, the electrons continuously lose energy on their way through the material, through the air, between the radiation source and your reference plane where you want to determine the operational quantity. Therefore, in beta dosimetry, this folding of spectrum and conversion coefficients is not undertaken, but the basic quantity, absorbed dose in tissue or HP0.07 in tissue, is multiplied by a correction factor, which was determined by means of simulations. So you see here, again, as outlined before, now I'm looking for the laser pointer, as mentioned, it's slightly delayed. You see here the reference depth 0.07 millimeter in the tissue slab forms the basic quantity HP 0.07, or 3 millimeter deep in the slab forms HP3. So this is the absorbed dose in this tissue slab, the reference dose. And then considering the different quantities as outlined before, you determine the dose and the different tissue depths here in these phantoms, and the ratios as shown here are then used to be multiplied with the absorbed dose measured, and here you end up with operational quantities. For these phantoms, well-known phantoms of current base, according to ICIU 57, and accordingly, using the new phantoms for the new quantities, local skin dose and dose in the lens of the eye, according to ICIU 95. So these phantoms are used here in these radiation fields, and the reference is always the dose in the tissue slab, full tissue slab, because this is what you measure with the extrapolation chamber. Just to shortly mention, you were not able to see this in the beginning. These phantoms, according to Iciu 95, have not only tissue, but in the front, the 2 mm slice of skin material. That was according to Iciu 95. So just a short summary regarding the primary dosimetry of operational quantities. The good news is that the procedures remain unchanged. The primary labs only need to apply new conversion coefficients or correction factors, which are by now all available also for beta dosimetry. So finally, you may want to wonder, which impact does this have to beta quantities and beta dosimeters? Assume a perfect dosimeter for the current quantity. This is not a perfect dosimeter, but assume it is one. Then its response with respect to the current quantity, HP 0.07 and the rod phantom were unity here. And you may wonder what will be the response with respect to the local skin dose according to Iciu 95. And the answer here, the response will be slightly larger, up to 30%, depending on beta mean energy and angle of incidence. So usually you will not have to worry about beta ring dosimeters. They will work in future fine if they did so regarding with respect to the current quantities. This is very different for islands dosimeters. Again, assume an islands dosimeter for the quantity HP3 in a cylinder phantom. If it were perfect and had a response of unity for all energies and angles of incidence, then with respect to the new quantity, absorbed dose and length of the eye, you have, depending on the angle of incidence and the beta mean energy, a significant over response here, up to more than a factor of 4 for normal radiation incidence, 0 degrees. And then this moves down further to here below 0.5 for 75 degrees angles of incidence. And this will not be sufficient, will not be well enough, of course, according to the response limits 0.71 up to 1.67, which are the limits according to the relevant IEC standards here for active and passive dosimeters. So beta islands dosimeters will very probably need modification. Or will need modification. Just to make clear, if you heard another presentation which says, well, no problem for islands dosimeters, yes, that's the case for photon radiation. So these are the same graphs, and you see here for photon energies of different radiation qualities, that's the ratio of the new and the old and the new quantities are nearly unity, be above 10 keV for ring dosimeters and islands dosimeters as well. So regarding to photons above 10 keV, there will be no changes necessary to ring and islands dosimeters probably, but for betas, there will be significant changes for islands dosimeters necessary. All these results are also published here for betas and here for photons, the latter together with Thomas Otto. The journey to implementation will be rather long. Firstly, international and national requirements and legislations will need to be updated. Then the ISO standard series for all particle types, photons, betas, neutrons will need an update regarding the new quantities. And finally, the ISO standards for procedures, maybe many more, and standards from IEC for dosimeters we need an update. So the implementation, if at all, will take several years, if not decades, I think. So we are nearly done. To sum up my presentation, I simply show the table of contents again. And as mentioned, we are nearly done. In the very end, I would like to give thanks to CCRI again for inviting me, to the Iciu working group reference validation fields for being allowed to lead the revision of the standard series, for Iciu for being member of the report committee 26, which prepared Iciu 95, and of course to several members of PDB staff of our whole department. I thank you very much. And I already see here in the chat there are 3 notices. Thank you.
Yes, thank you very much, Rolf, for this fruitful presentation. Thank you. I don't really see any questions in the chat, except will a copy of the presentation be made publicly available. And I know that the webinar itself will be soon at the BIPM YouTube channel. So it will be available in the form of video as it is. Yes, one more question. How can I get like a certificate of my participation with you? Probably it's the question to answer, but I'm not sure that such certificates they exist. It's just a public meeting, not a webinar for training.
No, there is no certificate given for participation to this webinar. They are publicly available, as you said, Anna, and nothing. I see there is another question in the chat for you.
Yes, will BSS2 need any changes once the standard upgrade is done?
Good question. No, thinking about this shortly, there will be no update needed because basic dosimetry will apply from then on, and you have your valid calibration according to the former standard version, and this will be in place as long as you use the standard. And in principle, the new updated version of the standard will not imply any changes of the dose rate, of the reference dose rate. Regarding the correction factors for the different photons and quantities, all these, as over the years were available in the open literature, they were already implemented in the beta secondary standard. So the BSS2 already considers the difference, for example, between the slab and the rod phantom, which is not the case in the current standard version, but already the case in the beta secondary standard. So this is some steps ahead, let's say, and therefore no additional update will be needed. If this is true, if you had a rather recent beta secondary standard. If you have very old ones, then you can possibly have a software update, and together with this, the new correction factors will be applied then also. Then I see a next question. What are the plans for the availability of new filters of the BSS2 system? Currently, there are no plans. I think you thinking of the 3mm and 4mm PMMA plate. There are no plans up to now because it is not so trivial. Up to now, the beam flattening filters, which are supplied with the radiation sources, are recognized by sensors in the beta secondary standard already. But these 3 and 4mm PMMA plate, there's no additional sensor available yet, and therefore it will not be trivial to implement this if you are talking of this. If not, please correct me. And,
yes, and there is one more, yes.
Yes, would there be, Rodolfo, would there be a potential implication for active personal dosimetry? Well, active personal dosimetry, to my knowledge, really, yeah, approved and well characterized dosimeters are only available for the whole body, measuring as an add-up HP 0.07. Other active personal dosimeters, for example, an active ring or so, I have no knowledge about such dosimeters. To my knowledge, they are not available, so there will be only minor, if at all, implications to the new to active dosimeters.
That's probably the addition to the question about the filters. We can supply only. We can supply our own 3 and 4 millimeters PMMA plates, but there will need to be an update to software still about the filters.
It's a good idea. Up to now, this was not planned. If you place such a plate in front of your source, 3 or 4 millimeter, then you needed to correct the dose rate also by applying a reduction factor. But this will have us, significant uncertainty, because we perform measurements with different radionuclides, strontium yttrium sources, and we observed that there are different reduction factors present. So, but in principle, it will be possible to give reduction factor for all sources, together with a slightly larger uncertainty, as already as usual in beta dosimetry, and then this will be possible. But you will need to correct for yourself the dose rates. The dose rate will be given by the beta secondary standard, as if the plate were not there. When you place the plate there, you need to correct the dose rate by yourself, and the reduction factor is available in principle.
Thank you very much. I do not see hands. Oh, okay, one more. Are all primarily instruments for beta radiation constructed in the same way as the PTB instrument?
No, it's not the case. For example, the Japanese primary institute uses a slightly different extrapolation chamber, and that's the case, Anna, you know better, in Russia and also in Belarus.
Yes, we also have 2 chambers. One is similar to the PTB instrument, and another one is our own invention of late years. So we have 2. One is not the same, but in principle, it's also a burn chamber, but another geometry, a bit other construction. If you're interested, probably, I think it is mentioned somewhere in CCRI documents and CCRI NIM documents. There are references there. How much variations is there on the density of commercially available PMMA? The thicknesses of the filters will need to be very tightly controlled or not?
Rick, very good question. Yes, there is significant variation. This brings me to the fact that the best would be to perform own measurements with and without such a plate in front of your source, and determine the ratio of the available dose rate by your own. with an appropriate instrument. For example, a secondary ionization chamber with a thin entrance window will do the job fine. You need to make sure that you measure the betas, of course, and then this is fine. Yeah, very good, Rick. You are right.
Okay.
By the way, this is another reason why the beam flattening filters of different sources must not be mixed up. So if you have a beam flattening filter for one strontium 90, yttrium 90 source and for another one, you should not mix them up. The sources at PDB are always calibrated together with their specific beam flattening filter, and you must not use another beam flattening filter for another source. For this, you need a new calibration. This is exactly the same reason here.
Okay, I see the hand from Vincent.
Yes, I have a question, Rolf, about the simulations that you have performed, very detailed, and maybe I missed something, but how this simulation have been validated somewhere?
Good point. I didn't show this in the presentation. It was even already so long, but I didn't think of this. How to do it? So there were validations with measurements. Of course, they are published, and I wonder whether I put in another page in the presentation in the PDF file before we post it on the website, and then there will be some information regarding the validation. What about that?
Okay, good.
Good point. Yes.
Okay. Oh, one more. Yes, please add validation slide. That would be very helpful.
Yes, as just mentioned, we will do so. I will do so. I will add the validation slide. Yeah.
So
together with its reference publication.
Yeah, so Rolf, does it mean that you will provide the PDF file of the presentations and we will put it as a done label documents on the CCRI website?
Yes, in a few days or so.
Okay.
I will prepare the PDF with the additional slide, and that's it. Yeah, of course.
Yes, thank you very much. Yes, thank you. So no more questions as I can see. So I think now we need to thank a lot. Thank you very much, Rolf, for your participation. It was very interesting, fruitful, and from me personally, that you find time to take part in this event. Thank you very much.
We have one more question.
Oh, sorry.
Yeah.
Can you please? Yes, one more.
Yeah.
After a lot of things.
Yes. Can you please
explain yes.
again where the nonlinearity of the extrapolation curve is coming from? Non-perfect correction factors. Yeah, that's simply you apply many different correction factors as outlined before, and some of them may not be appropriate. If we want to take the time, especially for krypton 85, there was nearly always this nonlinearity in the krypton 85 extrapolation curve. The reason is probably the correction factor for sidewall perturbation, because in the past, these correction factors were determined indirectly by means of measurements. So you want to remove the sidewalls of the chamber, but during measurement, this is not possible. And therefore, Böhm in the past placed additional rings in front of the chamber, performed measurements, and from the signals with and without the rings of different thickness and different dimension, he deduced the corresponding correction factors for the sidewall perturbation. This is published in a, I think, PMB, Physics, Medicine, Biology paper by Böhm in the 1980s, early 1980s. And from these publication, correction factors were derived and implemented in the ISO standard, the current version. But to be honest, the problem is, including myself, I did not find any person understanding how this implicit method worked out and ended up in the correction factors. And also, you must consider this is an indirect method. You place rings in front of the chamber in order to mimic the behavior of the chamber as if the side wall were not present. So this is an indirect method, and especially for Krypton 85, it was always assumed that this will be a non-perfect correction factor in place there, and from this, the non-linearity came.
Okay, thank you.